Hello students, welcome to the course Verilog HDL. In the previous video, we discussed the 4-bit carry look ahead adder, and in this video we look at the last example. Okay, this is the new example we are going to learn in this unit, that is 4-bit triple carry counter. Okay, so its design is we have somewhat understood in the second unit where we are discussing hierarchical modeling concepts. Okay, so this example was taken. So ripple carry counter is built using 4 flip-flops, T flip-flops. Then T flip-flop is constructed using a D flip-flop and an inverter gate. Okay, hope you recall that. Okay, so again we will take up that same diagrams design. So what is new thing here is, so how we build the D flip-flop using gates. Okay, so this was something not there. Okay, so that we are going to show you here. So how it came, I am not able to do that. Okay, so just the logic diagram I will show you. From the logic diagram, how to write boolean expression, so you are familiar, right? So in the digital electronics part, so in the basic electronics as well as DSD, you have written that. Okay, if an expression given, how you write the logic diagram. Similarly, how if a logic diagram is given, you know how to write the boolean expression. Okay, so using that boolean expression, we'll write the lower level module of the D flip-flop. Okay, so remaining all it is same. So now it is more clear to you the concept. Okay, so we now discuss an additional example that is not discussed in gate level modeling chapter. So whatever we have discussed so far, it was discussed, right? Full adder, multiplexer. Okay, but this is not discussed there. So we design a 4-bit triple counter by using negative edge triggered flip-flops. Okay, so what is meant by negative edge? So during the negative edge of the clock, there is a change in the flip-flop status. Okay, that is negative edge triggered. We design it using Verilog data flow statements now, and we test it with a stimulus module. Okay, so the diagrams for the 4-bit triple carry counter modules are shown below. Okay, so this diagram we are going to show you the complete procedure including the stimulus module. So previous and all we have not shown because it was done same in gate level modeling, so you have to copy there. Okay, here starting from the design, Verilog description and stimulus module, everything we will go through. Okay, so this is the figure you have looked in unit 2, that is hierarchical modeling concepts. So this is the upper level module, that is counter using 4 T flip-flops, and this is a ripple carry counter. That's why the output of first T flip-flop is given as uh, clock to the next flip-flop. See this. Okay, similarly output of this flip-flop is given as clock to the third flip-flop, and the third flip-flop output is given as clock to the fourth flip-flop. Okay, like that it will continue for any n number of carry counter. Okay, so first it will be having clock first, and then clear will be given to all the T flip-flops, and then the outputs. Okay, so this is the upper level module. So just T flip-flop, we don't have any construct, right, to write a operator. So that's why we will construct one single T flip-flop so that we can call the 4 instances in this design. Okay, so now we will build the T flip-flop. So that also we have observed. So this is the figure of the T flip-flop built using a D flip-flop and an inverter. Okay, so D means delay flip-flop, so it is inverted, that is toggle flip-flop. Okay, so clock and reset is given, and then Q is the output, and the part of the Q output is inverter, that is given to D. Okay, so this is a part of the D flip-flop. So again in this diagram only one gate was visible, so that you can write the expression for this, no issues. But whereas D flip-flop, how you construct using, so for that you require, that's what we told, top level, top to bottom and bottom to up, right? So there are circuit designers, they do the each gates they will combine and try to build the D flip-flop. Okay, so understanding D flip-flop using gates, it is available again. Okay, so that I am giving leaving as exercise for you, because I have done for 4-bit triple carry adder. Similarly, you now find the design of D flip-flop using basic level gates. Okay, so I will show you one diagram here, so which is prescribed in textbook, so that I will just show you. So note down that, and based on that we'll write the data flow statements for the D flip-flop. Okay, so this is the diagram. So final figure that shows the D flip-flop constructed from basic logic gates. Okay, so now you can write the expression. Okay, so this is a little complex but very simple. Okay, so you have the clear signal, clock, and the deep link signal. Okay, so that's what there in D flip-flop as reset. Okay, now clear. So it is first NOT gates are used for C bar, and clock also inverted. Okay, so this is the NAND gates. So 6 NAND gates are there here. Construction using only NAND gates is there. So 6 NAND gates are there. Okay, so that means you have to use the NAND expression. So what is the thing, how they are connected, based on that you need to write. Okay, see the first NAND gate. So you have the S bar as the output. That means this is on the left side, which is equal to, you have to write not of AND. Okay, so not is this one, and then you have to write the two operands. Okay, 2 or 3, whatever, how many are there. So here it is 2. So that's why 2 operands. So you have to fill these operands where they are connected from the logic diagram, right? See here, this is connected to the R bar, right? So this signal came from R bar. Okay, so that is the first operand, and this is S, R bar and S. Not of that will be NAND. So this is the first expression. Similarly for second, it is a 3 input NAND gate. So you have one S bar here. Okay, so this is the variable we have taken. Another is C bar, which is connected here, and then another is coming from the clock of, not of clock. Okay, so you can write like this, not of clock expression. This also C bar, it is generated because it is used multiple times. Okay, so then third NAND gate you see. So again you have the S here, and not of clock and R bar. Okay, so these are the three signals for third NAND gate. Again fourth one, so you have the R here. Okay, and then you have the C bar, and then you have the D. Okay, so D is connected. Okay, so this is how you have to write the expression, R bar not of R and C bar and D. Very simple. Okay, so then this side, so the final. Okay, so it is flip flop, means normally it will be constructed using this is constructed maybe from SR flip flop. Okay, so finally it is made Q bar as the output. Q bar is always the invert of the Q. Okay, so for Q, what is the input here? One is S and another is the Q bar. Okay, so Q bar is the, okay, so this NAND gate is having 3 inputs now. So Q bar is the output and input is Q, and then this is C bar. Okay, so where they are connected, just note down, and then this is R. Over. So total how many expressions? These two, and then these 6. Okay, 6 plus 2, 8 expressions you have to write using assign statement. Okay, so for that you have to remember this diagram, or if you understand the logic behind this also, it is well and good. Okay, so this is, I will leave exercise for you how it came. You can search some Wikipedia or Google it. Okay, so you'll get this. Fine. So now we'll write the Verilog description for this D flip-flop. Then so start from ripple carry counter, then T flip-flop, and then D flip-flop. Okay, so for that you remember this diagram. Okay, so whatever I mentioned here, again I don't explain there because I have explained here only. Okay, so it is an exercise. Even you can pause here and you can write by yourselves. Okay, if you have understood after attending 2 or 3 examples, you are in a state now to write it. So better pause it and write it. So let it be mistake. Okay, so you have to learn by mistakes only. Okay, fine, I will continue. So you pause it and write the 3 Verilog descriptions. Okay, given the above diagrams, we write the corresponding Verilog using data flow statements in a top-down fashion. Okay, so top to down, we will write that fashion using data flow statement. First, we design the module counter. So we'll be having 3 Verilog modules. So first we'll write for counter using 4 T flip-flops was there. Then the T flip-flop will define the code contains 4 T flip-flop modules. Then T flip-flop will call the D flip-flop and NOT gate, and then D flip-flop is constructed using the 2 NOT gates and 6 NAND gates, right? So like that we'll proceed, and finally we'll write the stimulus module. Okay. Okay, so this is the program we have seen earlier also, but that time it was not more clear to you. Okay, so now you have understood the operators, ports, everything. So this is now more understanding compared to unit 2. Okay, so in hierarchical modeling concept I have written this. Okay, or in the case of unit 4 while discussing the modules I have discussed this. Okay, but it was not more clear to you. Now it is clear to you. Okay, so module name was counter. I have given q. So this is the main. Okay, so this is the main program. Okay. Q, clock and clear. So you can look at the diagram of there. Okay, so clock, clear are the inputs, q is the output, and it is 4-bit output, q0, q1, q2, q3. It is declared as vectors, and input is scalar, clock and clear 1 bit. So what we have done in counter is we have instantiated the 4 T flip-flops. Okay, so the module of name is T flip-flop. Okay, so TFF0 is the instance name. So first T flip-flop, you had the Q of 0 output, clock and clear as the input. Similarly, second flip-flop, TFF1 name was given, and Q of 1 is the output and Q of 0 is the clock. So this clock was only for first T flip-flop, and this output will be given as input to next flip-flop, right? Clear was given to all the 4 T flip-flops, right? So then second T flip-flop, you had the Q of 2 as the output, Q of 1 as the clock signal, and third last flip-flop, Q of 3 is the output, Q of 2 is the clock signal. Okay, so these are very simple, no need to. Okay, so when you write this program, so now Verilog this one simulator will look for where is this T underscore flip-flop, because not is in a, it is not an inbuilt Verilog description. Okay, so that's why for that we need to go for next T flip-flop. We need to define after the end module. Okay, so after writing the end module, you have to start new module with T underscore flip-flop, same name. Okay, there is no change in the name. Okay, so T flip-flop is constructed using D flip-flop and NOT gate. For that you refer the second diagram. So next we write the Verilog description for T flip-flop. Notice that instead of the NOT gate, a data flow operator bitwise NOT negates the signal Q which is fed back. Okay, so this we are going to use instead of NOT gate. Okay, so this is an edge trigger T flip-flop and toggles every clock cycle. So module name T underscore flip-flop. So if you look at the diagram, what you have there, Q, clock and clear. Maybe I have reset, I think. So you make it clear. Okay, so because to make it uniform, so we'll keep clear. So in the T flip-flop, maybe it is reset. Okay, if it is reset, you write it reset here or make it clear in the diagram itself. Okay, then output Q, input clock, clear. Okay, so all are scalar here. So now we'll instantiate the D flip-flop and we'll call the D flip-flop. Okay, because it is not, it is constructed using this one. Okay, so edge D flip-flop, flip-flop 1, Q, not of Q. So there are two semicolons are there. Okay, so don't worry about this. Okay, so Q, not of Q, clock and clear. Okay, so this is what passed to the thing. Okay, so Q, not of Q, clock and clear is passed to edge D flip-flop. That means this is a new user defined program I have written over here, and now this is constructed using the gates, the third diagram I told you know. So that's why, so counter using T flip-flop, T flip-flop using D flip-flops. So that D flip-flop is using now this one. Okay, so here some comments are written for this. Instantiate the complement of output Q is fed back. Notice Q bar not needed, unconnected port. Okay, so here Q bar was not there. Okay, so QB. Okay, that is not required, unconnected port. That's why it is kept here space. Okay, so both comma is allowed. Okay, so you should write as it is. Fine. Hope you note down this. Okay, program. I will go to next slide where I will discuss about the edge D flip-flop constructed using 2 NOT gates and 6 NAND gates. Okay, so that program we will look at. Okay, so that is the end of the Verilog description. Finally, we define the lowest level module D flip-flop using data flow statements. The data flow statements correspond to the logic diagram shown in figure above. The nets in the logic diagram correspond exactly to the declared nets. Okay. So this is a program module HDIP. So the same name you should give. You should not change with a single letters also, even capital also not allowed because it is case sensitive. Okay. So the same name is given module D HD flip-flop. And what are the inputs and outputs you have in that? You have to write Q bar are the outputs at the end you had, right? And D clock and clear are the signals as input. Okay. So that is passed. So then it is declared here output q bar, input d clock, clear. Then there are some intermediate variables we have used in the gates, right? So that we need to you declare using wire. Okay. So S bar, R bar, and the output of clear is C bar. Okay. So these 5 signals are declared as wire. Okay. So now we'll start with the data flow statements. We will create a complement of signal clear first. That is the first signal C bar equal to not of clear. Okay. So this is used many times. That's why it is defined. Whereas clock is not done, because straight away we can give the not of clock in the design itself. That's why for that again separate assign is not done. Okay. So hope you understand this basic steps. Very simple, as it is same in all the programs. Okay, fine. So we'll go to the next one where we will write the complete that NAND gates implementation. Okay. So input latches, a latch is level sensitive. The edge sensitive flip flop is implemented by using 3 SR latches. Okay, so this is implemented using 3 SR latches. So one SR latch means 2 NAND gates connected, cross connected. So since 3 SR latches, so you have 6 NAND gates. Okay, so that part of the implementation we will begin. So first assign you have. So just look from the top one. Okay, so S bar is the output. So NAND gate is used. This is how we use not of R bar and S. Okay, equal to S bar, not of that. That means NAND gate. And we can write continuously assign like this. Instead, we have used a comma operator here. Okay, so that means you can many statements you can write it in a single line. Then you have the S, which is equal to the 3 input NAND gate. So not of S bar and C bar and not of clock. See here. This also we can write. Since it is a unary operator, this will be computed first, operator precedence. Okay. So not of clock, and then it will be ended with the remaining signal. Okay. So for this again, we didn't took another wire and we have not made not of clock. Even if you have done, no problem. Okay. But this is how you can do. But C bar we have done because it is connected many places. So maybe we call. Okay. So both example it is tried to show you. Next we have the R output there. Okay. Third NAND gate. So it is also NAND gate. So not of R bar, not of clock, and S. As I have mentioned in the design, the same thing I am writing here. So fourth NAND gate, the downmost, you have the R bar is the not of R, C bar, and D. Okay. So this just AND means it is a AND gate. So not of AND gate is NAND gate. That's why negation is kept outside. Okay. Then finally we have the right side two NAND gates. So Q and Q bar. So assign Q equal to again NAND gate. First one is 2 input NAND gate. So S and Q bar are the inputs. Okay. And then Q bar you have. So again we have comma operator use 2 statements we have clubbed here. Not of Q and R and C bar. Okay. So final statement we will keep the semicolon C here. Okay. And the module. So this is the program of the 4-bit ripple carry counter T flip flop and D flip flop using 3 SR latches is done. Okay, so now we have to write the stimulus module for this. So all the inputs, the counter, okay, main program only we will call. So these all and all we will not take into picture. Okay, so what you had there, clock, clear, and the Q output. So that values we will give and write the stimulus. So stimulus module, the design block is now ready. Now we must instantiate the design block inside the stimulus block to test the design. Okay, testing is very important. Okay, the stimulus block is shown in example below, and what you observe here is the clock has a time period of 20 with a 50% duty cycle. Okay, so time period 20 means what? So one cycle. Okay, up and down, that is one cycle. So what is this 50% duty cycle? This is we are using in lab also. So duty cycle, how you define, which is nothing but a the how much time this clock was on. Okay, so this is the one clock period. How much time it is on, that is called as T on. Okay, divided by total time. Okay, period T, or we call it as T on plus T off. Okay, equal to 100. Okay, in percentage we will call. So now it is, if it is equal distance, okay, normally you will have clock of equal distance, right? So here my diagram is changing, but it will be equal distance when you have, so then you will have 50%. Okay, So for example, this if you consider t on equal to 2 second, okay, and t on is 2 and t off is also 2 second, that means 2 seconds it is on, 2 seconds it is off, so it will come 2 by 4 means 1 by 2 of 100 is 50%. Okay, so that is the duty cycle we will using in when we are using waveforms. Okay, so hope you remember this. So now we'll implement the stimulus module for this. Okay, so module name stimulus, it does not have any list of ports. Okay, then inputs will declare as register, as in the earlier case, register, clock, clear, capitals I have used just to differentiate. Wire 3 is to 0 q, even if you use the same also no problem. Okay, so then monitor statement is written first here. Okay, anyhow you can write, even the this also you can write first here, instantiating the design. Okay, initial monitor dollar time count q equal to output we are noting and we are passing the values of input clear. Okay, so clock is automatically generated, so not it is given. So that means counter, it is keep on changing the value. So clock will give start initially, clear will make it is reset to 0. Okay, it is counting 0 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15, after that it will 0. In between when it is reached 7 you may reset, so it will again start from the 0, not from 8. Okay, that is the idea of clear. Okay, so now the design we are calling, its name was counter module first program. Okay, module counter, for that instance name is given c1 and it's passed here q clock clear, so it is given in the same order, that's why it is connecting ports by ordered list. Okay, if it is by name, dot operator was used there. Okay, hope it is understood the stimulus module. After a long time you are looking at the stimulus module again. Okay, then we'll have the clear signal, how we change it, it's clear signal. So beginning, so we'll make it 1 bit 1. So you remember this timing because we are going to see the simulation output how it is going to change. So initially it is made clear 1 bit 1, that means up to 34 time minutes it does not work as a counter. Okay, so as we made clear equal to 0, so it will keep counting. So again at 200 we will make the clear equal to high 1 bit 1, and after 50 we are going to make it 0. Okay, we can write the finish also, but finish we have written as a separate one. Okay, because if we give it here we have to add it. If it give from another initial, that means it is 0 plus that. Okay, so here it is 0 plus 234, 234 plus 200, 234 plus 50, 284. So finish should be given after 284. Okay, so we'll write it in separate initial block. Okay, so see here, set up the clock to toggle every 10 time minutes. So now we are writing the clock signal. Okay, so clock 1 bit 0 forever, every 10 time minutes clock equal to not of clock. Okay, so meaning what? So every 10, that means what happened to here t on, it is 10 and here 10, so duty cycle is 50%. Okay, that is the idea of duty cycle. Finally we have to simulate, I told you after 284 only you have to stop. So here given 400, you can stop at 300 also, initial begin 400 finish. So what is the difference? Instead of writing this as a separate module, you could have written the finish in there only. How? By just making how much difference is there. So 284 was there last, for that if you have to give 400 means 116. Okay, so dollar hash 116 dollar finish, this statement you should write instead of 400. Okay, if you write the same dollar 400 finish there, it will add up 284 plus 400. Okay, but we have to stop at 400 time minutes, that means it is a new block, so it will start from 0 here. So 0 plus 400, it is 400 time minute, it will stop. So just to show you in stimulus module, so how the waveforms will work. Okay, for that taken this example. Okay, fine. So we'll write the simulation output for this. So hope you have understood, note down this. Okay, so simulation output starts from 0. Okay, so see here how it looks. So initially clear was 1, so that's why counter is 0. Okay, till 34 time minutes it is 0 only. Okay, because clear is just made 0 at 34, but there is a delay right in the gates. So after counting that from 40 it is trying, because it should look for negative edge, right? So here clock is there something, right? 10, 20, 30, 40. It should wait for the negative edge. See here, this is the negative edge comes at 40. That's why till 40 still it is 0 is there. Okay. So when it reaches 40, so it starts counting. See here, 0, 0, 0, 1. Okay. So and clear was 0 up to 200 time minutes, right? So now it is keep counting at every 20 time minutes because negative edge is available next 20, right? 40 is over, 50 is positive edge. Okay. Again at 60, you are getting the negative edge. So it will change the output now 00012 to 0010. Next at 80, at 2020 you will get. Okay. So 100 you will have 0100. At 120 you have 0101. 140 you have 0110. 160 0111. This also you can draw it in a waveform. So the some of the tools are available, right? So CAD tools we are using, so it will build the waveforms for you. Okay, so just for our understanding in notebook, here we are using this conventional way of writing monitor statement. Okay, 188, 200, 9, 220, 1010. Okay, so till it is 11, right? So 9, 10 it is counted, right? Still counting was there 15, but what happened here is at 234. Okay, so what you have made clear equal to 1 you have made. Okay, so that's why what will happen, so count will reset to 0. Okay, and this will continue up to 284 where you made the clear equal to 0. So still it is 0, but exact when it will become, it is at the 300. Okay, so just at 280 there was a negative edge, 240 there was a negative edge. So next was 300. So it will again start counting 0 1 2 3 4 5 like that. It will continue again. If you make clear one, so it will reset. Okay, so just to show you this idea, this waveform was shown. And at 400, okay, so 400 time minutes, so it is not written, right? So up to 380 it will count. So at 400 it is finished. That's why the last value was 380. Okay, so 400 negative edge it will stop. So that is not shown here. Okay, because it is not going to do anything, stopped, right? So waveform is not coming. So this is the idea of the 4-bit triple carry counter built using the data flow operators and stimulus module we have observed. Okay, so in the next video we'll summarize the what we have learned in data flow modeling, and we have some 3 exercises so that we try to solve one by one. Okay, so with that we are completing the module 3 also. Okay, fine. So we'll stop here and we'll continue in the next class with the exercises. Okay, thank you.